Hello and welcome to another video. In this video we're going to be doing the hard problem from contest 380, which is find beautiful indices in the given array 2. And this is going to be the same exact thing as the second problem in this contest, but the constraints are tougher. So if you can solve this problem like this, you should be able to just copy paste the code into the other one and it should work. So in this problem you're given a 0 index string S, string A and string B, and integer K. And this is kind of confusing what they kind of mean. So let's kind of walk through exactly kind of what it means. So basically what it means, this I is beautiful thing, is let's look at example 1. You're basically trying to find every index where the string matches A, and then you're trying to see, is there an index where the string matches B, and is that difference less than or equal to 15? So if we look for my, there's a my right here, and there's a squirrel right next to it, right? So this index is going to work, and I think this is 16 because there's a my right here. So this index is my, this index is squirrel, so obviously these are within 15. And there's also a my over here, and the squirrel over here, they should be close enough to each other, right? So 16 and 33. And they basically tell you, so here's 16 and 33, and that's why that is. Let's look at the second example. So A is A and B is A. So if the strings are the same, then every time there's a matching string, obviously it's going to give you that. So this is going to be this index 0. And basically the hard part of this problem is you need to figure out, and once you do this, you kind of solve a problem. You need to figure out all indices where A matches string, all indices where B matches string, and then just check for every index in A that is a match, is there one in B that is close enough to it? And we can figure that out, how to do that. That part's pretty straightforward, but the hard part is, and if you've never done string hashing or KMP, you basically have to know one of those to do this problem. So that's kind of what we'll go over here. So let's look into the difficulty of this problem. Notice that the constraints are 10 to the 5th for S and A and B. So if we look, like here's like let's pretend this is string S, let's pretend this is A and this is B. So if we actually tried to match this string here, what we'd have to do is we'd have to start at the first character and have to check like, okay, is this equal to this? No. Okay, then we have to start at the first character again. Is this equal to this? Yes. Is this equal to this? No. Okay, start at the first character again. Is this equal? No. Is this equal? No. And now these two are equal, right? All these characters match. So we'd basically write down the index here for A. So this is going to be index 1, 2, 3, 4. And then we keep going, right? So this whole thing matches. So let's take this thing. Hopefully I can select it. There we go. And then now we try over here. No, 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 no. And basically it's going to be no up until this location as well. And so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, whatever. Let's just call it 18. So let's say this is location 18. I didn't index it because it's kind of like a long array. So let's just pretend this is index 18. Doesn't really matter. I think we might actually be able to look here. It should be the same. So it says it's 16. So let's just go with 16. Okay. And now, so these are all the locations where squirrel matched, right? We have 4. And let's pretend this is 16. I'm not sure if that's exactly right, but either way, it doesn't matter. Whatever this is. So now that we match that, now we basically have to do the same thing for the other one, for my, right? So we'd have to start over, and we'd have to, in worst case scenario, remember these strings are 10 to the 5th each. So imagine if your strings almost match, and then there's like a 1 character difference. You're basically going to have to try to match the whole thing, and then if it fails, then you have to start at the next character. So this is like an n-squared solution. So it's like, no, 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 no. And then there's a match here, which is, let's say this is 14. Not exactly sure, but let's just use those numbers. And are there any more my's? I don't think so. So these are the two locations where it matched, right? So, whoops. So they matched at 14, and that's it. And this one matched at 4 and 16. And let's pretend, let's go see what K is for that example. I don't think I made this string like as long as the one in the example, but close enough. So K is 15. So K is 15. Then you can see that like both of these characters are close enough to this character. They are less than 15 away, right? Basically, what you have to do is you have to say, okay, for every character that I found in A that there was a match, is there one in B within 15, right? And there is one here because 4 and 14 are close enough and this is close enough. So then you would return 4 and 16. But our problems are, what if this is a lot of characters? What if this is a lot of characters? Like, how do we get this quickly? That part we'll go over at the end. But the main concern is, how do we do this string pattern matching quicker, right? We can't like go character by character, because if we go character by character, we have to, worst case, it would be n squared. We have to get an O of n or something solution. And like I said, there's two ways of doing this. There's the KMP, and KMP relies on figuring out where strings intersect, so you don't have to like do this in an n squared way. And it's kind of complicated. You can look up KMP, but there's another way, and that's the string hashing algorithm, and that's what we're going to go over here. So let's take the squirrel, right? What we can actually do is we can actually make a hashing function, and I did this in a previous problem. So the way it works is we can take a hashing function, and let's pretend this is indexed. So this is indexed like 0, 1, 2, 3, 4, 5, 6, 7. So we can actually take this squirrel and we can get a hashing function for this, and we can calculate it. And there's a bunch of hashing functions, but a really easy one is you take your index. So first, actually, you take the ASCII value of your character. So ASCII character times some prime number, let's call it p, to the index. You can either do to the index or to the index plus 1. I think index plus 1 is more common. So basically, the example here would be like, for this character, this would be, and I don't really have enough space here. Maybe I can make it bigger. So let's do that. Let's make this a little bigger, and then we can fit the actual like thing in here. So let's do this. There we go. Okay. So what this is going to be equal to is it's going to be ord of s, right, in Python, times, and whatever language you're using, just get the ASCII value, times the index plus 1, and you need some prime number. And so really common prime numbers, if you want a good hashing function, you can look this up, like prime numbers for hashing functions. A really common one is 131, but it's going to work with a lot of prime numbers. So you just take 131 to the index plus 1, so in this case, it would be to the 1. Then this is going to be that value of this character. Then for the next character, it's going to be this, right? So it's going to be ord of q times 131 squared. And then you're basically going to have this repeated thing, right? Ord of u times 131 cubed, and so on. And so basically you add up all of these things, right? You get all of these values for every single character, and then you add it up and you get some value. So we get some hash value. And the other thing is you want to keep your hash value small, so you can make an integer, and this is where it gets a little bit tricky. You can make an integer mod, which is like the common thing in all these problems, just this. And anytime you're adding these hash values, just make sure you like keep reducing so it never gets above mod, right? So anytime you're adding these and take powers and so on, you just keep like modding it by this. So you get some hash value for a, right? Hash value for a. And like I said, if, you know, let's say a is like 4 characters, it would be like character 1 times p to the 1 plus character 2 times p squared plus character 3 times p cubed plus character like this, right? So you get all that, you get a value. Then basically you can do the same thing for this string here. And you can actually compute this using prefix sums. So for a particular prefix, you will have all of these added, right? So for like this character, it's going to be the same thing. This character times that prime number to the 1, this character times prime number to the 2, and this is the value for all of these, and then you just do like a normal prefix sum. Like imagine you're just adding a bunch of values, you're doing a bunch of prefix sums, and then for a particular string, let's say I wanted a string from here to here, I can take this value over here, right, this prefix, minus this prefix, and that would give me the hash value for this section. And basically now what that allows you to do is, let's say I'm looking for squirrel. So I'd figure out, first of all, like how long squirrel is. So in this case, squirrel is 1, 2, 3, 4, 5, 6, 7, 8 characters. So 1, 2, 3, 4, 5, 6, 7, 8. So I'd start here, because this would be like the first viable end index where I would match. And then I would check, what's my hash value here? And if my hash value for this index, and because the prefix for like this is just 0, right? So the prefix for this square that doesn't exist is 0. This should equal this if this is squirrel, right? If this was actually squirrel, it would be equal. And then if it is, you write down the index. And remember, if you're checking here, this is the end index. So the index you'd actually write down would be this current index minus the start of it. So you would actually write down this index because that would be the start index of squirrel. Then if it is or isn't, you go to the next one. Same thing, you do a prefix, right? So you do this prefix minus the prefix that's 8 characters away, right? So we want 1, 2, 3, 4, 5, 6, 7, 8. So we're going to subtract this prefix here, right? So if this is like P2, P1, we would do P2 minus P1, which would give us this section here. And then we check, is that the same as squirrel? But now here is a small problem. So for this whole array, remember I said this is like character times p to the 1, character times p to 2, character times 3, and so on. So for a particular chunk, like imagine we just have this chunk, right? Let's say we're getting this chunk. We're not doing squirrel, but let's just say we're getting this chunk. And let's pretend this is index, one index, let's call it 10, and this is 14. Obviously, doesn't have to be, or it should be 13. So the problem here is if this is the rolling hash that we want, the actual values in these 4 blocks would be like this character times p to the 10th, plus the second character times p to the 11th, plus the third character times p to the 12th, plus the fourth character times p to the 13th, right? So if I did have a string of length 4, my string of length 4 would have a hash that looks like this. So how can I compare to this, right? This is totally different. And so you can do this. You can do it one of 2 ways, right? Basically, I need this to turn into this. So this is just like a math problem. How do I do that, right? And there's 2 ways to do it. You can either take this whole thing and divide it by p to the 9th, right? Which would basically get rid of 9 p's on all of them. So this would be 1, 2, 3, 4, and so on. And then you can compare it. But because you're modding at every step, dividing with mods is kind of tricky. So instead, what we're going to actually do is we're going to take the hash for the string that we're trying to find, and we're going to multiply that by the right amount to make it into this. And we can just do that based on the index, right? So if this has to be 1, then we can figure out like what index is this, and how much do we need to multiply this by, right? So we would need to multiply this by p to the 9th. And if we do that, then what's going to happen here is this will be 10, right? So basically you're adding 9 to all of these. So plus 9, plus 9, plus 9, plus 9. And now these, if the characters are exactly the same, will be identical, right? So that's kind of the trick. You keep going through and you figure out what do I need to multiply my original string that I'm checking for. This would be like string A, right? This would be like the squirrel that we're looking for, or the my or whatever. And then we basically use these prefix sums to figure out, like, we just maintain a window, like a sliding window of where the start and end of the string would be, and we just keep moving it one character down. So to look for this entire string now, in this big string, is just O of n. So first we needed to compute it, which would be like O of m, but then to actually look for it, now we're basically checking at every possible end character location. So we're basically like going through. Let's actually get rid of this and get rid of this and kind of show like this in the picture. Get rid of all this. So basically now if we're looking for squirrel, we're saying like, okay, let's line it up here. Let's check this hash value. Is it equal to this whole hash value? If it is, then we have the squirrel. If not, either way, even if it is or it isn't, let's keep going. And then we're basically, now we're only checking one index at a time, right? So we always check the last index. So we check here, we check here, then we check here, then we check here, then we check here. And we're basically doing a O1 operation now, because we're just doing a prefix sum there, right? We're basically just saying whatever we're at, find out the length of squirrel and take that minus the start part, and then also figure out what this original squirrel hash needs to be multiplied to look like this thing here. And so once you do that, basically what's going to happen here is you will get 2 arrays, right? So you'll get 2 arrays. So the first array will be the characters in A, like the start location of the characters in A that match completely. So in our case, I think our first word was squirrel, right? So for squirrel, let's say the start locations are here. And then for this, let's say this, let's actually do something more complicated. So let's say for our start locations of characters in A, we get like 4, 10, 15, 25. And for our start locations of characters in B, maybe we'll get like 1, 10, 30. And let's say K is 5. So this part is pretty straightforward. Basically, we have to take every character in A, and we have to say, is there a character within 5? But we have to do this efficiently as well. Like, we can't have this be n squared. Because imagine if A is like really small. Like, imagine if A is like my or something, and then B is like something else that's really small. And becomes very long, and this is also very long. So you have to do something efficient. And it's pretty straightforward how to do this part. Basically, for this 4, you would take all the characters in B, and you can just binary search through them to figure out if a character exists. So you would take the middle value, and you'd say like, okay, is that difference smaller or less or equal to K? If it is, I can just break out. And if it's not, then just figure out where your numbers are. So let's actually change this a little bit. So let's say we're looking for the number 25. Right, so in A, we're looking for 25, and our B, and remember this is going to be sorted. We're going to have a sorted array because when we look for these locations, we're going to be looking for them in order. So both of these are going to be sorted. So for A, we'll say like, okay, well, let's say the characters in B are 5, 15, 35, 45, 95, something like that, right? And K is 5 again. So we basically look like, let's just get, this is our array, and then it's like a basic binary search. So we take a pivot value, we say, is this difference K or less? No, it's not, it's bigger. And then is this value bigger or less than our A value, right? So this is our A value, this is our B array. If B is greater than A, then we know that like everything to the right is invalid, because if this is not close enough, then all of these are not going to be close enough. So all of these values are invalid. So now I just have to work with these, and then I'll get some pivot value here, and then I'll say like, okay, this is too small, right? So it's too small and it's too far away. That means everything, if there was stuff over here, would be too far away. So I get rid of this, and then finally here, this is too far away as well, so there would be nothing here. So you can basically do a binary search for the second part for every value in A, just binary search for a value in B that's close enough. And your value is either going to be close enough, or it will be too far to one side, in which case you go one way, or it'll be too far to the other side, in which case you go the other way. So that way, when you have these two arrays, this will be logarithmic, right, to get every single value. And yeah, that's basically it. So as long as you understand this like hashing algorithm, it's not too bad. And as long as you understand that you have to make sure that like these p-values coincide with the p-values of your original string. And in order to do that, you just take your original string, figure out where your start index is, and multiply your original string hash by the appropriate number. You can check, and then once you get these two arrays, it's just like a basic binary search to figure it out. So let's take a look at the code. Let's full screen. So basically, there are a couple edge cases, right? So if A is bigger than S, or if B is bigger than S, like let's say A is like banana, and B can be whatever, let's just say it's A, and S is like this. This can't possibly ever have a solution because banana can't be in S. Like A and B can't be in S if they're bigger, right? So if that's the case, just return. And then you have to use this mod value, and basically the tricky part is getting these hashes, modding by mod, and doing all the math correctly. The other thing is we're going to pre-compute all the powers of, like I said, I'm using 131 for my P. You can try other values. I think like 7 works, 3 works. But basically, for a good hashing function, the idea is you want to make sure you don't have collisions. So you want to make it like as complicated as possible so you don't have like false positives, right? So you don't have two words that hash the same thing even though they shouldn't. So for example, if you make this like 2, this is going to be wrong because, in fact, I'm pretty sure it's going to be wrong. We can try it right now. So if I make it like 2, because it's even, and it's very easy to get collisions, if I change all these 131s to 2s, so here, let's see here. I think that's all. We can actually just find 131, right? Okay, yeah, so that's all of them. So if we actually submit this, this should fail, theoretically. Right. And so the problem is we're getting like too many matches because our hashing function is too simple. So that's kind of like you want to draw a line between something that's complicated enough to where you don't get false positives, but something that's good enough. So you really want to make sure you use primes here, and then the bigger the prime, the better it's going to be. But obviously, the bigger the number, the slower it's going to take. So there's like some trade-offs there. The other thing you can do to make sure you don't have false positives is you can have two hashing functions. So maybe like you can use 131 as one value, and then you can take another odd number as the other value, and then you can make sure like in order for there to be a match, both of those hashing functions have to be true. That would be like a more complicated one, but this is fine for this. So we are basically just pre-computing all powers of 131, because remember, for every index, we're doing character times 131 to the index. So we want to pre-compute because we're gonna use this a lot. So it's like if you're gonna use a lot of powers of something, you can just pre-compute the whole array right off the bat. That way, because getting a power of a number, and if the power is a really big number, is actually logarithmic. It's not linear time. So pre-computing is going to be faster. So pre-compute everything. Then we have a function that gets the hash for a string. Pretty straightforward, like I said. So this is literally, you have a total, you go through every single index, and you add the previous total plus the ASCII value of our current character times the power of our, so this power I plus 1 is basically saying it's 131 to the I. So it's actually to the I plus 1. So if I is 0, this will be like 131 to the 1. If I is 1, it would be 131 to the 2, and so on. So this is just the pre-computed values. Then we, like I said, we want to keep making sure that the total is small enough, and that's the other important thing. You want to keep modding all your stuff by mod, and you want to be pretty good with modular arithmetic. So this will essentially, we can put in A and B in here now, and this will give us a hash value. Then this is the function that we have that we give it a string, right? The string that we're looking for, and the value of the hash of that string. So we'll pass in like string A, and then the hash value of string A. Then we want to get the length of that string, and we want to get our result array. And like I said, the first index we want to start at is, like, let's say we're looking for apple, and our string is something like this. The first index we want to look for is here, because we're looking for end indices. So for this index, if that equals this whole thing, then we have a match, right? And we start here because we need this whole left thing to actually be able to fit the word. So we look here, then we look here, it'd be like this part and this part, and so on. So it's linear time. So we basically get a temporary hash for our string. And then we want to get the hash for our current index. So this is that prefix sum difference, right? So this is basically the prefix. And in my prefix sum, my prefix sum is one index because I made prefix of 0 equal to 1. You can use a dictionary and make it easier, but basically it's just basic prefix sums modded by mod. And then you have a multiply factor for your string, because like I said, you know, if your string is like p to the 1, p to the 2, p to the 3, p to the 4, but when you're matching, you're like over here. Now these values are going to be like, you know, p10, p11, whatever those are. You need to take your original string and make it line up with these, right? So if this is like p10, p11, p12, p13, and your original one is like 1, 2, 3, 4, you would need to multiply all of these by p to the 9 to get that. And so that's basically what we do here. So we figure out a factor. If there is a factor, then we multiply our old hash by this factor power thing. Then, well, like I said, we mod it again. And if there's an equality, then we just append the start index for that string, right? So if the hashes are equal, like let's say we are over here, and the hashes are equal, which they would be in this case, this would be squirrel, then the index we would want to append is this one over here, right? So we're comparing end index hashes, and then for end index hashes, we can just figure out based on the length of the string where the start index hash is there. And yeah, so we do this for A and B, and we'll get two arrays. It's actually this function over here. So this will give us our two arrays, and then we just have a basic function that takes an index I, and this is determines, is there a beautiful function here, right? So this is what we're going to use when we have our two arrays. So let's say we have like 1633 and then like 4 or something. We're going to pass in all of these into this is beautiful function, and then each time we will basically binary search through this B array and figure out, like, is there a value that's close enough? If there is, let's return true. If not, let's return false. And the rest of it's pretty straightforward. So we get the hash for string A and string B. We get the whole prefixes for the entire string S. Then we get the A indices and the B indices, and we just return a list of all A indices that are beautiful. So we pass them all into here, and we check, is there a B index that's in there? And so we can run that. And I do think this is pretty complicated to code, and if you've never done string caching before, I think this is definitely good practice. It is kind of slow. I think it runs, when I ran it, it's anywhere from like 3,500 to like 2,000. So when I looked at other people's solutions, they were, I think, a little bit faster. And I think KMP is a little bit faster, but KMP is not super intuitive. I feel like string hashing is a lot more intuitive, but you can also check out KMP. You can just like YouTube KMP, and there's a bunch of like videos, but it's also kind of a complicated hash function. But either way, you basically either have to know string, you basically have to learn either the string hashing. I forget the name of this. We can take a look. Let's see. This is called. I was looking at some of these. So yeah, so there's this KMP one, and I think this one is called. Let's see it. Let's see. Let's just look for all. So it is a rolling hash, but there's a it's called this like Robin Carp hashing. So you could look for that. So I basically looked at I think before I looked at some other solutions for string hashing to learn the string hashing, and then you can basically apply it to this problem here. And this trick that I showed you, this little factor, lets you compare a string to any string and like any substring quickly, right? So now you can basically compare substrings in O1. There is also another problem if you want. And you can Google it too, but there's like find like a needle in a haystack, where it shows like KMP and all that, and you can practice it on that. And that basically just gives a string and a substring, and you're trying to find if it exists. So you can definitely practice the rolling hash in that problem if you want to for practice, and then if you get all that right, then try it in this problem. Yeah, so we can look through the run time for this. Also going to be pretty confusing, I think, but let's take a look. So this part is nothing. Pre-computing powers of 131 is just going to be O of the length of the string, because we're just doing that for the length of the string. So that's already O of S. Getting the hash for the string is going to be O of A and B. But because when if A and B are bigger than S, we're just returning. So you can argue this is still going to be like upper bound O of N, because A can't be bigger than S, and B can't be bigger than S either. So that's O of N. And then this find hashes thing is O of N as well. And then this beautiful thing is basically a binary search for each of these. So however many there are. So I think it ends up. I think the reason it's a little bit slower is because it's n log n, because this find hashes thing needs to actually find these. I think KMP actually has to do this too. So maybe you could do this with like, I think people did, right? They did like some kind of sliding window or something. So there might be a better approach to doing this like beautiful part thing. Like once you get the hashes, once you get the two arrays, you might be able to just do like a sliding window instead of a binary search, which will speed it up. I haven't really looked into that because this problem kind of took me a while. And that's not like super important. Like that part you can figure out. I think the main takeaway is just learning string hashing from this. Yeah, so you might be able to speed it up. You can try it. And yeah, and the space. So let's take a look. So we have this prefixes, right, for the string, which is O of N. And then we also have this power precompute, which is O of N. We have the hash for each string, but that's just a variable. So that's nothing. So I think this is just O of N, right? Because you basically have the prefixes and the powers. And these are also worst case O of N, these two arrays, right? Like worst case, it's never going to be exactly O of N, but it can be like O of N over 2 or O of N over 3 or something, which will be O of N anyway. Yeah, so I think that's going to be all for this one, and definitely kind of an interesting one if you are looking to do string hashing. I think this is pretty rare. I did do this in a previous contest, like 2 or 3 contests ago, where I did some like I think it was like the palindrome problem, where you have palindromes and you can swap letters. That was the same kind of thing, where you have this hash, same kind of thing. So if you saw that video, this basically the same kind of algorithm, except the only trick is, like I said, to have a factor to multiply your stuff by to make it equal to the thing here. Because in the previous problem, we had 2 arrays and we were just comparing things at the exact same index for both of them. So we were comparing something for this array at this index, and then we had an array of the same length, and we were comparing that string at that index. So you didn't have to like multiply by anything there. So there's just like one other thing here. And yeah, it's going to be all for this one. So if you did like this one, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.